Hey, and welcome back to the lab, where today I want to take you with me on my journey on refurbishing this nice Hewlett Packard 3400A RMS multimeter. And the beauty is, even it is this special unit is 39 years old, but this meters has been built from the early 50s, I believe. So this is still an RMS voltmeter which can't be beaten by today. So this meter has the highest Crest factor still in the world, and therefore it is really awesome to have a nicely meter acquired. So you see this shape is nice. So I've already taken off here the housing to get inside, because I mean, it is clear, if you buy an old meter like this, you need to do some maintenance. So we have capacitors which are now almost 40 years, and then this meter is not able to hold the specs. So therefore we really have to do something, and that means we need to swap out some of the capacitors, since I have tested the meter for some specifications, and one very important spec is what is about the supply voltage inside here, our meter. And I've recognized that one of these voltages was quite noisy, and if a very important supply voltage is really noisy, then you can't expect that the meter itself works perfect. So even it is working, we need to do, as I said, some maintenance. And therefore I've already received here a bag of new capacitors, especially here for this meter. And yeah, therefore let's go step by step, and let me show you what I found, because it is again very exciting, because I've done a couple of months ago videos about ESR, and what I've done here first was testing the ESR, and I've recognized that we have one capacitor which has really a very high ESR, and we have always the discussions, is a high ESR really an indication that something is wrong? And of course, after I have tested for ESR, I've taken the capacitor in question to my capacitor analyzer, and let me show you what I found. Okay, first of all, that you know what I'm talking about. So we have here three very important supply voltages inside our meter, and beside here our voltages, which of course needed to be in spec. We have additional to that here our ripple specifications, and you see that it is required 400 microvolt RMS or 1.1 millivolt peak to peak, and the same here with our plus 75 volt, and we have 2 millivolt peak to peak with our minus 6.3 supply voltage. So you see we have requirements, and I have really seen right from the beginning that something was wrong here with our ripple specs. So therefore I started to look after the capacitors. And look here, so that is our power supply, where we have the filter capacitors which are in question. So look here, we have here our C1 where we have a double pack, 240 microfarad, and we have a filter resistor in between, so that is a whole filter, if you like. And so that is 1.1 volt peak-to-peak ripple maximum, which I've seen that we was a lot of above this specs. And the second one where we had to look after is here our C2, which is a 890. So you see that this is a very old spec for a capacitor, as well as a 40. So that is not what we have today. So 890 microfarad, and yeah, so we have to test this. And well, let me show what I have found. Yeah, and down here we have here our double pack capacitor, and we see here the resistor in between, and I've already taken off here the wires to be able to test without something connected to this pole. And of course we have here our power supply PCB in front, so that is inside here. Anyways, the first what I really did is I connected here my ears ammeter to it, and that is what we are gonna do right now as well. So this here is ground, and this here is one cap of our double pack. And yeah, reading here the ESR tells me that we have 9.3 ohm, and we all know that is quite too high. The other cap in the pack is here, and it is still connected to the rest of the circuit, and you see that looks okay, so not too bad. Let me double check. Oh no, it is also 8 ohm. So you see that both capacitors inside this double pack are out of spec. And I thought, okay, maybe that does not really tell us something. So let's go over to my Sencor Capacitor Analyzer, and let's try to verify what we found. And according to our specs, let me first put in the capacitor values. So that is an aluminum electrolytic, so that is already dialed in. And according to the specs, it is a 200 volt type, and it is 40 microfarad. And now it gets interesting. It is plus 30% and minus 10%. So that are the specs. So 200 volt and 40 microfarad. So that now is all programmed into our Sencor. And now let me connect the leads, and let me see what the Sencor is telling us. Okay, so you see my Sencor is connected to the unit, and our dear EE is not connected any longer. So let's go over to the tester. Okay, so first capacitor value 14 microfarad, and we have a 40 microfarad in, and that means it is bad, and that is what our unit is already telling us. Then let's see what is the ESR. and it is 12.7, so this meter is showing a bit higher ESR, but again bad. Alright, and now what is about the leakage? So we have now our test voltage already dialed in, so you've seen that, and now we test for leakage, and let me double check what a capacitor with 40 microfarad and 200 volt should show maximum, and let's say yeah, between 70 microamp and let's say 110 microamp. So that is the maximum what it should show. So let's test. Wow. And you see it started, it is going down, but it is millivolt. It is millivolt. It is absolutely too high. So we should have maximum 100 microvolt. And you see it is absolutely too high. Okay, let me check the other side. Let me just put the clip on the other side of the double pack. And let's see what we find now. So I've connected it to the other side. We do exactly the same capacitor value. 20 microfarad, so maybe a little bit better, but again it should be 40, and of course it is bad. Let's see what the capacitor ESR is. 10, which is bad. And now the same, let's check for capacitor leakage. No, I can't do that because it is still in circuit, and I do not want to jeopardize the meter, so I do not check in circuit the leakage because we are testing with 200 volt. We have to take it out anyways, and therefore we can do a final test of the old capacitor afterwards, but I believe you already have seen what it meant. If we find a bad ESR, we always should go for a deeper analysis, and I can promise you, for 98% you find what we have seen just in this case here. So therefore, let's go ahead and let's prepare for swapping out this capacitor. Yeah, and here I have a replacement type. So that is a double pack as well, 47 plus 47 microfarad. That is a 350 volt type, and I hope that I will be able to fit it in. So let's see how it works out. So I've taken out this this piece of metal to get access here to our capacitors. So that is double pack 40 microfarad. Don't know if we can read it. It is difficult. And down below, so that is our 890 microfarad, but that is only a 15 volt type. So of course we have to test that as well. But here let's start with the faulty one. And just that you can see the difference, so I have the new one connected here to the meter. So let's check capacitance. 48 microfarad, which is fine. I have to place it here a little bit better when we go with 350 volt. And let's check the ESR. 2.4 ohm, so that is okay. And now let's check the leakage current, and you see it starts with 16 milliamps and just goes down, so that we already get here our good indication. So that is good, as you can see. And we have 95, 80 microamps, 79, and you see that it is still going down, and that are microamps, and it is still going down. So if the capacitor is in circuit, so you see that it is going down into the 50s, into the 40s, 37, and you see now it is at its final value maybe. So you definitely see the difference what a good capacitor is and what our bad one was doing. Okay, and as you can see, we have our new capacitor in. So, and of course we have a new resistor instead of this old one here, which I do not really trust. So this is a modern metal oxide type, which is really nice. And then of course, oh, you can't see it there, down there we have, where is it? Ah, over there. So there is our new capacitor, and that is nicely in. So we can go ahead. Okay, and I'm testing here our C2. So that is the 890 microfarad. So which is plus 100%. So it can have really the double of 890. And we are reading 1183 microfarad, which is fine, tested with 120 Hertz. So that is a new norm, and this is definitely not a capacitor according to the new norm. But anyways, we have here a nice value. And now when we switch over to ESR, and of course we have to test it with 100 Hertz, we have 0.19 ohm, which is for an old capacitor nice. So the only question is, all values are fine, as you have seen. We did not lost any capacitance. So the only thing what of course we need to test is if we have a leakage. So let's connect our capacitor analyzer as well, that we can perform our leakage test. Okay, and let's see what our leakage is. So 15 volt, that is important. Capacitor value 1245, so that is almost the same what we have seen before. And now what is our leakage? And 268, good already, microamp, and you see it is dropping. So that is always important to see that of course our leakage current is dropping, and you see it is really nicely dropping, and therefore we definitely can say that it is fine, no doubt. And because the specs are telling that we can increase our capacitor here up to 100%, I put additional 330 microfarad in parallel to increase the capacitance to a higher level, because a bit higher level would hopefully give us a little better ripple and noise. So therefore I put here an additional Panasonic high performance capacitor in parallel, and what we see now with the second capacitor in place, we are approximately at 1.5 micro 1500 microfarad, which is quite nice. And when I'm switching over here to ESR, then we see that we have 0.044. So because I have set here one capacitor in parallel, we can decrease at the same time the ESR. And well, so I would say that is a very nice solution. We can keep our original capacitor. We support it a little bit, but in any case we have seen that all figures were just fine. So we could have left him completely alone, but I think that might be even a better solution here. Okay, and as already discussed, we have here all new capacitors, and well, I believe that some of those capacitors here on the power supply board will be fine, but having in mind that it is 40 years old and that is a test equipment, so a high performance test equipment, and therefore it is definitely nice to have finally something new here in or on our power supply PCB. Okay, after we have replaced our capacitors, especially the one which we found having a capacitance loss and a high ESR, so now we are at the test points which are showing in the service manual, and you remember the maximum ripple and noise we should have is 1.1 millivolt peak to peak, so that is 400 microvolt RMS. So that is really a tiny signal of ripple and noise, and to really test a voltage which is so small is really not easy. It is not easy with an oscilloscope, because normally you would need a differential test head to do so, and to do it with a normal probe, as I'm doing it here, is really critical, and you have really a lot of things to consider to get, if you like, a more or less reliable reading. So believe me, that is not easy. But let's look over to the scope. I had to do all the settings manually, because otherwise it is no way to probe this little signal of ripple and noise. Okay, and here is what I'm probing. So using these both lines to test the vertical difference, and that is by minus ay. So that is what we see here, and you see it is really small, and the peak to peak level is 620 microvolt. And yeah, you see, and that is you see how sensitive it is. So that happens if you really only get away from the test point. So it is really critical to test such a tiny signal. But you have seen our peak to peak level is 620 microvolt, and allowed is 1.1 millivolt peak to peak. Okay, so you see now it is not connected, and you see if or how really sensitive this is here. So you really have to be very careful to do here the reading without a real ground connection, and a short it is not possible. So you cannot really take this ground leads here, right? Because that is more an antenna than anything else. So you never would be able to test. And even if we do it with this ground connector, still there are so many influences into probing such a low tiny signal. So as I said, normally we really would need a differential test head, because we have so much common mode signal which is really going here into our measurement, so it is critical. And what I've forgotten to say is that those tests need to be done in AC coupling, right? And of course the bandwidth limit needs to be set to 20 megahertz, because that are the requirements. Because remember, we are having here DC voltage on this test points, and therefore of course we need to adjust here our scope to AC, because we do not want to test the AC as a DC. We need the ripple and noise, and that is AC of course. So therefore very important to say. Okay, all DC voltages are now in spec regarding the level of the DC and regarding the maximum ripple and noise, so everything is fine. But if we look here to our needle, let me see if we can get it in. Yeah, maybe you can see it. So it still has a little jitter. So therefore there is still another little issue which we need to fix. I mean, we have to have in mind that the whole unit is not shielded, and normally all tests should be done shielded, but yeah, so I just saw that, and well, we need to have a look after that. I mean, it is only a little bit, but maybe we can improve it. Okay, so far everything has been done concerning capacitor replacement and so forth and so forth, and I have put the housing back to the unit, because that is a requirement for alignment. And now I'm going through the alignment procedure step by step, and let's see that it all works out nice. I mean, that is here the first test, so it is set to 400 Hertz on the signal generator and 1 volt RMS output, and that looks quite okay, but there are some other settings which are obviously misaligned, or maybe there is still another fault which we hopefully find when we start now the alignment process. And by the way, the jitter here of the needle is almost gone. It is just a little bit still, but that might be normal. So it is such a little jittering that you almost can't see it. So I would assume that is okay, but on the other hand, we can check the shopper IC, which is an operational amplifier. So that is something we will decide when we have performed the alignment, that we can get a good reading. Okay, I'm already here in the alignment procedure, and I have already aligned the amplifier offset, which is here on the A6 board. So that has been done, and I have performed already the amplifier gain adjustment. So that has also been done. So one point for the gain adjustment is that I read 1 volt here at the back side. So there is a DC connector which puts out a DC proportional to our meter deflection, and so you see I have the 1 volt, but still I do not have here my full meter deflection, because we should read 1, which is stands in the 0.01 position, so that means 10 millivolt is full scale, and the generator is putting out 10 millivolt RMS, and also everything has aligned correctly. We need now to align for full scale, and there is another alignment down here, and that is R6, and that is full scale adjustment, and that is what we want to do right now. And you see I'm moving the needle, as you can see, to our 1 or full scale position, as you can see, and that is now our 10 millivolt reading, which is now working perfectly. To show you what it means to have the amplifier offset right, is when I take away here the input signal, and you already see it even without here the input a little bit not shorted. I also could shorted it completely, and you see that the needle here is really almost on 0, which indicates that the amplifier offset is now perfectly aligned, and we do not see here any noise, right? And back now to our input, 400 Hertz, so low frequency adjustment, of course, and now we have really here 10 millivolts. So now let's proceed. Up to now it is working nice, so no other fault to see up to this alignment point. Okay, and you may see that the needle here is going over our 1 in the moment 1 volt range, and that is because I now have to align the 1 volt setting, and I have I'm feeding in 1 volt 400 Hertz, and this is now not optimal. So we need to align here on the side, as you can see here, our R104, so that is a 1 volt 400 Hertz alignment. So let me prepare that, and then we see how that works out. Okay, as you can see, now I try to get it here back to exactly 1 volt. I cannot really see it. That is a little bit too much. Let's see. Okay. So now I'm exactly on 1 volt, so that looks good. And you see, that is really something you need to do in peace and quiet, because it is always critical to do those alignments. But what you see as well is that it really turns out nice. I'm going here really step by step, and you see I'm able, up to now, I'm able to align everything absolutely against you know, our manual, which is a good sign so far. Okay, so I had to stop the alignment process. So we have seen that everything was quite nice with our low frequency adjustment, which is at least 400 Hertz. So that is what you here see as well. So that is our 1 volt alignment. And now I was going over to the high frequency alignment, and I recognized that I was not able to align the same output level on the meter for 10 megahertz and 3 megahertz. So I had a really huge difference between these both frequencies, and that is you know, not normal. And I thought, there must be a problem somewhere that we are not able to align here on our video amplifier board. So we have this cap here, which is responsible for the 10 megahertz alignment to get at least 10 megahertz and 3 megahertz, and that means over the whole range, to get more or less the same output level. And that is what this capacitor is for. And it was not possible. And so I started probing around, and besides the fact that I've seen that already a new capacitor has put in, and that is definitely not a right capacitor for this purpose here, because you always have the risk that it is shorting out here. But other than that, look at this resistor here. No, you can't see it. Sorry, let me go over to the meter, and that is ohm, all right? Nothing else but ohm, and I have 2.5 ohm for a capacitor, which is definitely wrong. I mean, for DC, a capacitor is high resistance, so no current should flow. So therefore, let me take that capacitor out. Okay, let me do it that way. So we have here now our capacitor, which is 200, don't know if you can read it, 200 microfarad and 30 volt DC. And you already see here on my meter with 120 Hertz, which is, as we all know, the right test frequency for capacitors. We have 5.3 millifarad, which would be over 5k microfarad. So that is already odd. That is not possible. So therefore, let me go over to ESR, and on ESR, and there we know we have to test with 100 kilohertz, and that looks for the first moment good. So 0.29 is not too bad for a 40 years old capacitor. But so we could misinterpret this value and would call this capacitor as fine on the first glance. But, well, when we then go over to our DC testing, so that is now a simple DC ohm test mode, and you see we have almost the same what we had on our Keithley, and therefore 1.3 ohm is a short, and that means this capacitor is toasted, right? And I mean the old Spark are known for it, and yeah, you know, that is the problem, one of the problems why the 10 megahertz alignment was not possible. So what I really want to point your attention to is the fact that if you have a fine ESR testing, that could mean, on the other hand, that there is a hidden problem on DC. So you also, or you should always test the DC values, or a normal ohm testing should be taken place as well. But you need to know what you are doing, and let me show what I mean. Okay, so look here, that is our impedance converter, right? The A2 board. And look, our C203, which is our 200 microfarad capacitor, is here. So that is a bootstrap feedback, right? And now I have put my normal ohm meter to the both pins of the capacitor, and I was reading 1.5 ohm, which is wrong, of course. But what you need to have in mind, so there could be always, you know, a pass to ground, or there could be a lower resistor in parallel. So you always need to watch out in which situation this capacitor is in this dedicated circuit. And what you can see here, okay, this way, capacitor, no DC. Capacitor, no DC. Here, our little tube, no DC flow. Here, a 10 kilo ohm resistor. Here is 3.3 mech resistor. And here is a transistor. Even if this transistor would have a short to ground, then if we test between these two leads, it should, in any case, even if this is shorted here, you should not see a resistor of 1.5 ohm, because it should be high resistance. And therefore, that is important to double check what's going on the board, and always have a look into the schematic to evaluate if what you read on your meters could make sense or not. Okay, and after I have really swapped out here all the Spark capacitors here on our impedance converter board, and of course on our video amplifier as well, I was preparing everything back for our 10 megahertz alignment. That is what we found to be difficult because of our shorted capacitor, right? So I recognized when I was preparing everything that suddenly our scale and value was varying. So the needle was moving back and forth from one test to the other. Also, nothing has changed here really at the input. And I was really wondering, what is that? And then I started once again our alignment for our operational amplifier here. So that is, if you will, our operational amplifier for driving here our needle, if you like. And since that is an older operational amplifier, we have here a manual offset alignment. So this pot here is the offset alignment for our operational amplifier, right? And I recognized when I was trying once again to align my offset that you really recognize that when I only was touching it just a little bit with the screwdriver, that I really had a huge movement on my meter here, which is not normal. I mean, sure, you really need to be really gentle to align those offset things. That is for sure. But that when I only touch it, that I see that the needle is moving, that is definitely not normal, even it is a higher quality potentiometer what you have here, right? So I'm really certain that something is wrong here with our potentiometer. So I'm really going to let's see if I can get in here really a precision type. So then it is even more accurate. Or if I have finally moved to, let me see, I should, yeah, I have to go to a normal version which we have inside. So I try first the precision one to have the most accuracy while I'm aligning this offset. And because I'm already working here on this board, I'm swapping out here our chopper operational amplifier, or chopper amplifier, since we have seen this little jitter on the needle, and it might be that the old one, 40 years plus, which is in here, is a little bit too noisy. So I hope that with a newer one and a more modified version, it will be less noisy, and therefore let's try this as well. Okay, so what you can see is that I put here a precision IC holder in, and I've gotten here my precision potentiometer in, which is quite nice. I hope that now the needle should be rock solid after our alignment, offset alignment, of course. And well, you see I have here the new 7650 IC. So that is here the older one. No focus. So that is the older one, and so 40 years old, and that is the same 7650, but a modern, improved version. And I truly hope that that will be less noisier, and yeah, we will see it when we have it in for testing. Okay, so I've changed the IC as described. I've changed the potentiometer as described, and I have swapped out a bunch of old capacitors to new. And well, I have followed the alignment process, which is really tricky, I have to admit, but now see what we have, and that is awesome. And I will really explain why this unit really still have that high value, even it is that old. So have a look. We have here in our display 10 millivolt. So you see our switch here is set to 0.01, which means scale end is 10 millivolt. And you see it is 10 millivolt. Oh, by the way, have a look what here our jittering is doing. It is rock solid. So the new IC, which was, as I told you, a more modern type, is awesome. So you see it is almost nothing. So that is great. Anyways, so again back to what I wanted to show you. So 10 millivolt, and the needle is exactly showing 10 millivolt. Okay, and now you may ask, hey, that's nothing really exciting. So 10 millivolt, so that is what any good meter can show. Okay, so let me show you what I'm feeding in. Okay, so first what we see is I'm feeding in a pulse. Okay, so that is not that much exciting. But you see I'm feeding in a pulse of 100 millivolt peak. And we have seen here on our meter, scale end is what the needle is pointing to, but that is 10 millivolt. I'm feeding in 100 millivolt peak. Okay? And you see the reading on my meter might be wrong. Is it really? Okay, let's deep dive into that. And then you may understand why a high crest factor is what we are looking for, and that is what we need for some special measurements. Okay, what have I done here? So we have a frequency of 10 kilohertz. Okay, and we have a pulse width of 1 microsecond. Okay, 10 kilohertz is 100 microsecond. So that is the whole waveform. Okay, 10 kilohertz, or we can say 100 microsecond. And the pulse is only 1 microsecond of the 100 microsecond which our entire pulse is. So the signal. Let me go over to the scope. Maybe then you see what I mean. Okay, that is exactly what we are getting out of our signal generator. Okay, so that is 100 microsecond. So the pulse from here to there. So that is 100 microsecond. Okay, and the pulse itself is only 1 microsecond. So what we can read here, so 1 division is 20, I hope you can read it, microseconds. So we can count, if you like, 20, 40, 60, 80, 100. So that is definitely 100 microsecond. And only 1 microsecond of 100 is where we have a pulse. So I can spread it here a little bit if you like. So then you see here our pulse. Okay, so that is a pulse. But in reality, or in relation to the whole waveform, right? It is only 1 second from 100. So you see, that is really a short while where we get this pulse. And what you can see as well, it is really 100 millivolt peak. Okay, so you see what that means. So we have only a very tiny moment, a pulse, and that is the importance of what we are talking here. And again, we have seen that we are feeding in 100 millivolt peak, okay, and we are reading here 10 millivolt, but what? It is not 10 millivolt peak. So what this meter here is reading is RMS. So, and that is really the awesome point what this meter is delivering. So this meter is able to deliver the real RMS value of, and now let's go back for a second, RMS. So normally when we are talking about AC, okay, we may think of our main wall plug AC frequency, which is in the US 60 Hertz, in Europe it is 50 Hertz, and we know, okay, that is AC. And then you see that we have today in our modern world, it is not really difficult to have multimeters which are reading the so-called true RMS. So the older multimeters which were on the market, so back, I don't know, in the 60s and earlier, of course, in 70s as well. So a multimeter was most of the time not able to read the RMS, a true RMS. That means this meters back in the 60s or so was only able to read the real RMS as long the signal what you are feeding in is a crisp and clear sine. If it is something else, then all the meters started to struggling. Today, here on modern meters, you find always true RMS multimeter. So that means if the sine is varying from a clean and crisp sine, so if it is something else, like noise, which is, and I believe we all can agree on that, that is not a clear and clean sine. So that is something else. But a true RMS multimeter is able to read the RMS even if the signal we are probing is not a clear and clean sine. Okay, that is very important because in real world, so let's say we are probing on audio applications, so you never have a clear and clean sine, but you are really wanted to read a real RMS value because that is from interest. Okay, and now let's go back here to our scope and to the signal which we are feeding into our HP-3400A RMS voltmeter. So we are feeding in a signal which is, and I think we can agree on that, is far away from a sine. So that is anything else, but it definitely have nothing to do with a sine, okay? But a meter like our HP with a very high crest factor is able to read the real RMS out of what we are feeding in, so our pulses, okay? So let me demonstrate what it really means if we want to find the real RMS out of the signal we are feeding in. And we are now feeding the same signal where we tested at our HP 10 millivolt RMS. Now we say, okay, we have here an AC millivolt meter, so it goes from 2 Hertz up to 12 megahertz. So that seems to be fine, and it is set to 10 millivolt, as you can see, scale end. Same signal which I've fed in the HP. So now let's feed it in here in our Philips meter. Okay, so look at this. Can you see this? Can you see this? Once again, we are here at 10 millivolt. It is exactly the same setting. It is an AC millivolt meter. It is reading from 2 Hertz up to 12 megahertz. We are feeding in a signal of 10 kilohertz, which is definitely within the range. And look what our meter is showing. Almost nothing. It is really almost nothing. So normally we should see our needle on the 10 millivolt setting. We really should see the needle at the end of our scale, because our RMS value of our pulse is in reality 10 millivolt. But you see, this meter is completely failing, and it is not able to read the RMS value. And it is not even close. It is really saying, okay, I'm struggling. I do not know what I'm getting feeded in. So total fail. Okay, and here I'm back at my HP. So here is the signal from our signal generator, our pulse, and see what happens. And of course, it takes a little while until the needle is really at 10 millivolt. Okay, so that is taken a little while, because the meter here is only able to deliver the real RMS, because the meter is using thermal couplers, and that is the only way to get a real and true RMS value. I do not want to go into thermal couplers, but let me say this is only possible simply because this is using here thermocouplers, and of course the circuit around the thermal couplers needs to be really accurate, designed to be able to deliver what the meter is doing. So out of our 100 millivolt peak pulse, the real RMS is 10 millivolt. Okay, now you can say, hey, Peter, you can really tell me a lot. Is that really true? Okay, if you like, let's have a look into that. Okay, let's look at this old publication from HP. And the title, as you can see, is the significance of Crest factor. So that is what I always told you, that Crest factor is really important to be able to do good testings. Okay, now I do not want to go through the whole equation here and taking that here all together to get to the final result. So if you are interested, it is from HP 9049, 9098. So that is from HP, and it is called as you can see. And here we have this experiment what we built here on the bench. So you see our signal, so the pulses 100 microseconds, the whole signal, and 1 microsecond our pulse. So they describe what a signal could look like and what we need to take into account, and they run you here through all the mass to determine at the end what, if you put in this signal, right, what the real RMS of this signal will be. So I have really looked deeper into that, but we do not want to do it here. Just let me show you 2 or 3 points out of here, and that is here that D is equal to TO over T, okay, which is at least, if we go to this little graph, so we see T and TO, okay, that is according to this D, so that is important. And if we know D, and if we know EPP, which is like volt peak, if you like, so here you can see it, EPP, okay, and that is what I've shown you on the scope, right? And if you have that figures, then you can use this formula. ERMS is equal to EPP, and then root D. Okay, so that is all what we need. And when I now go and take the figures we were working with, so you see 1 microsecond over 100 microsecond is equal to 0.01. You can do it at home. Take your calculator and check it out. We have seen that ERMS is equal to EPP root D. Okay, D is here. So that means we have put in a signal amplitude of 100 millivolt pp times root 0.01, which is that here, okay? And the root 0.01 is 0.1. So now we take 100 millivolt peak times 0.1, which is that here, and that is at the end 10 millivolt RMS. Okay, So you see 10 millivolt with our 100 millivolt peak amplitude, and our signal of 1 microsecond to 100 microsecond is exactly 10 millivolt. And that is exactly what we are reading here. And that is awesome. So the meter is absolutely doing its job. Okay, now you can ask me, what do I need it for? Well, it is not old days that you need it, but there are some special tests which are really easy to perform with exactly that meter here. So I have told you at the beginning of the video that it is tricky to do noise measurements with the oscilloscope, because normally you need differential test heads which are very expensive, and still then you have to consider really a lot of different parameters, so you really could do many things wrong. And on the other hand, you could handle if you use two inputs on the scope. Okay, you can use two inputs, and then you use the mass function, which is possible, but it is really tricky. This here is a meter where you really can do that with. But still, where do I need it? Well, one very interesting test is to check your DC power supplies. Okay, how does that goes together? A DC power supply is DC, okay, not AC. So why do I need a RMS voltmeter? Okay, we all know that power supplies have noise, and that is called on power supplies, it is called as ripple end noise. Look, and this is here my power supply, and now let's check out the specs. And in our specs we can find it. So here that is our ripple and noise, and that is another very, very important figure. So noise tests will always be performed within 2 Hz up to 20 megahertz. Okay, check out here our scope screen. Look here. So that is our bandwidth limit, and it is set to 20 megahertz. So you always perform noise testing within this frame from, let me say, 0 Hertz up to 20 megahertz, because we all know noise can be everywhere. And that is the reason why modern, even, you know, a high value multimeter, for instance, can't read it, because even the best multimeter does not go up to 20 megahertz. That is the reason why even here our Keithley is not capable to do those tests. But now let's go back here to our chord. And you see our ripple and noise within this bandwidth will, or claims to deliver, a ripple and noise below 2 millivolt RMS. So you see, we are talking about noise, and noise is far away from a sine, but the value which is given is in RMS, so we need at least a meter which is able to read RMS. So let's check out our power supply. Okay, I have here connected my power supply to my HP. And remember, our power supply specs were claiming that the rippling noise is below 2 millivolt RMS. And you see I've set here our meter to scale end of 3 millivolt, okay? And now it should be below. It should be below 2. And look where we are. So here is 2, because the lower scale is the valid one. And now see where we are. 2.1, 2, 3, 4. It is almost 2.5 millivolt. Here, what the power supply is delivering, and that means our power supply is out of spec. I mean, that is fine here for most of the applications I'm working with. But on the other hand, you see our power supply is definitely not fulfilling the promise of below 2 millivolt, okay? And you see clearly it is above. And here you see our Philips AC millivolt meter, and the Philips meter is certifying our power supply to be within the specs. So you see we have set it to 3 millivolt, so that is the same setting as we did it here on our HP. And you see here it is fulfilling the spec, and you see now how important it is to have the right test equipment for the right, or for the dedicated, if you like, tests you need to perform. And if you use this meter, you would say, okay, it's fine. But if you go over to the HP, you see, no, the power supply is not delivering it promises. You see how important it is. And of course, even with here our HP-3400A, we still need to think about some little problems you need to consider if you are probing, because we really need to think about common mode rejection, because it is not protected against common mode distortion, as for instance a differential test head for an oscilloscope is protected against common mode distortion. So we don't have it here, but there we can help a little bit, but that is definitely another video and not this. So the only thing I still wanted to tell you, if you are asking, hey, where for do I need it? Okay, we have seen testing the power supplies, but okay, power supply in the lab, it is important to know that it is not horrible noisy. But on the other hand, if you really have a very expensive radio, let's say for instance the Kenwood TS990S for instance, which is quite an expensive radio, or a Hilberlink, or the top flagship from Icom. So those radios are 10, 12,000 euros. And of course, in radios like this, you have local oscillators, which really needs to deliver local oscillators, which very low phase noise level. So we are talking about minus 120, minus 140 dBc. Okay, and of course, if your radio has a good local oscillator, but you have a problem with the power supply, which is finally supplying those local oscillators, then the best local oscillator does not help, because the noise from a faulty power supply will really damage your whole performance of this high value radio. And to do analysis on those radios, you really need something like this to check out what's going on with the power supply, for instance. So you see only two examples. You can also use this as nice analog meter to do your radio alignments. So you know, I'm normally using here my Philips PM2554 for doing radio alignment, so that is a fantastic meter for that. And you can of course use the 3400A even better for alignments. So there is a bunch of varieties where you can use this meter, so that is excellent, and it is really a nice addition to my lab. And I hope this video gave you some insights for special test equipment, which is really dedicated to some very, very sensitive requirements. Okay, so that's it for today. I hope you learned something, and catch you next time. Bye.